Welcome back to ECE 501B. In this video we are concerned with finding singular values of an operator, and we will do that by first stating the definition of singular values. Then we will state a theorem that allows us maybe an easier way to compute these singular values, and then we'll actually walk through an example illustrating how we can find singular values of an operator and what that might look like in a particular case. Here's the definition of singular values. It's definition 49 in chapter 7. And it says, given an operator T on some vector space, linear vector space, capital V, and we could say that that has dimension n if we want to refer to it as a specific dimension. The singular values, which I'm now representing as lowercase s sub I, of this operator T are actually eigenvalues of our positive operator T dagger T, or the square root of T dagger T, the positive operator, the square root of T dagger T, with each of those eigenvalues lambda of this positive operator, square root of T dagger T, repeated according to how big the dimension of the null space of lambda I minus the square root of T dagger T actually is. Those m sub i's, you could have a two-dimensional null space corresponding to a given eigenvalue lambda. You could have all eigenvalues just having a one-dimensional null space, and then all of the m sub i's would be 1, and you would sum up those m sub i's, which in that case L would be equal to n, and we would just have 1 plus 1 up to n, where n is the dimension of V. We might not have, or we might have repeated eigenvalues of this positive square root of T dagger T operator, and that's what I'm meaning by m sub I. Maybe one of those is repeated twice, maybe another eigenvalue is repeated 3 times, and maybe one is not repeated. So we might have 3 eigenvalues, let's just say equal, then let's say the one-dimensional is an eigenvalue of 1, the two-dimensional is an eigenvalue of 2, and the three-dimensional is an eigenvalue of 3, then we would have singular values of the operator T equaling 1, 2, 2, 3, 3, and 3. An easier way or strategy or technique for finding those singular values, we could invoke Theorem 52. And this is finding the singular values without actually having to use this square root of a positive operator. Remember, a positive operator enjoys these nice properties that give us these non-negative eigenvalues. Let T, again, be a linear operator on our standard vector space V. The singular values of T, again denoted by s sub I, are the non-negative square roots of the eigenvalues of T dagger T. So now we're worrying about the eigenvalues of T dagger T and not the eigenvalues of the square root of T dagger T, but obviously there's a relationship or connection between those. Here, if we compute the eigenvalues of T dagger T, we actually have to find the square root, the non-negative square roots of those eigenvalues in order to assign those as our singular values of the original operator T. And again, we have the same null space dimensions associated with the appropriate eigenvalues, and that allows for repeated eigenvalues of this positive operator T dagger T, which means that we would also have repeated singular values. Let's now work through or discuss an example from the textbook. It's example 50 in chapter 7, and it begins with the assignment of a linear operator T in a 4-dimensional space where we're saying T maps this 4 vector, z1, z2, z3, z4, into an output vector 0 for the first component, 3 times z sub 1 for the second component, 2 times z sub 2 times for the third component of the output, and the fourth component of the vector of our output is minus 3 times the input fourth component z sub 4. The matrix representation then of that linear map, you can see that the top row of the matrix representation, since the first component of the output vector has to be 0, that whole row is 0. The second row of this matrix representation of T simply needs to pull off the first component of the input vector and scale it by 3. We can do that by this second row in our matrix representation of T. Likewise for the last two rows. The third row in the matrix representation of T is simply taking 2 times the second component of our input vector. And finally, the last row in our matrix representation of T is going to simply take minus 3 times the fourth component of our input vector. Now I could ask you the question, what is or what are the eigenvalues of this matrix representation of T? And what you should start to see immediately is that this particular matrix is lower triangular. We have all zeros above the diagonal and only non-zero entries below the diagonal. And since it's a lower triangular matrix, then that means that we can actually find the eigenvalues by looking on the diagonal of that matrix. And for that reason, then, the eigenvalues of this matrix are 0 and minus 3. We have repeated eigenvalues. We have 3 eigenvalues at 0, so these are repeated 3 times. And by inspection, we found that the eigenvalues were 0 and minus 3 because we had this matrix representation was actually lower triangular. From this matrix representation of T, and since we're dealing with the standard basis, which is an orthonormal basis, we can find the matrix representation of the adjoint of T, and that's just going to be the transpose of this matrix representation, which becomes then the following matrix. In order to find the singular values, we can either use our definition and find the eigenvalues of the positives, or of this operator defined by the square root of this positive operator t dagger t, or we could use Theorem 52 and simply take the square root of the eigenvalues of the positive operator t dagger t. In either case, we need to form, or we can form t dagger t, but before we do that, let's just remind ourselves of how we could go from this matrix representation of the adjoint of t dagger into its linear operator. And that is found by looking at the first row, and that says, oh, we just form the first component of the output of that adjoint operator by scaling the second component by 3. The second component of our output scales the third component of our input by 2. We zero out the third component, and the fourth component of our output is going to scale the fourth component of the input by minus 3. There then, in the lower right hand corner of this screen, is our linear map associated with the adjoint of t. If we now formed the matrix representation of t dagger t, here is t dagger and here is t. if we look at this, we can see that t dagger t, the first row is going to simply be taking 3 times the second row of t. So that's now going to be 9, 0, 0, 0 for our matrix representation of t dagger t. If we now look at the second row of the output of t dagger with t, we see that we need to scale the third row of t by 2, and the third row of t is just 0, 2, 0, 0. We scale that by 2, and we obtain 0, 4, 0, 0 in our matrix representation of t dagger t. The third row we just annihilate. Since we're hitting each of the rows of t with a weighting of 0, the third row in t dagger t is just going to be the 0 vector, or the 0 row. And finally, if we look at the fourth row of t dagger t, we simply take the fourth row of t and scale it by -3. We then have -3 times -3 in the 4, 4 entry and 0 everywhere else. And this now gives us our matrix representation of t dagger t. We can find the eigenvalues of this very easily because this is a diagonal matrix. We have an eigenvalue of 0, an eigenvalue of 4, and 2 eigenvalues at 9. If we now used our theorem 752, we could immediately find the singular values of t from those eigenvalues of t dagger t by taking the square root, the positive square root of each of those entries, and that ends up being 0, 2, 3, and 3. Or we could find the singular values of t from this definition, which requires us to find the eigenvalues of the square root of t dagger t's matrix representation. The linear operator associated with t dagger t is easy to find from the matrix representation of t dagger t. We're simply weighting the corresponding coordinate in the input vector by 9, 4, 0, and 9, and that's now our linear map associated with t dagger t. That is pretty clean to find the square root. In some cases it's not so easy, but this example was cooked up, and so it's easy to find the square root of that particular operator t dagger t. From the definition, then, we can find the eigenvalues of the square root of t dagger t. We have 2 at 3, 1 at 2, and 1 at 0. That means then that the singular values of t are 3, 3, 2, and 0, and that is then what we wanted to find, and that's consistent with the singular values found by looking at the top row on the screen right now, which concerns the eigenvalues of the matrix t dagger t. And those were then using those, we take the square roots of those to obtain 0, 2, 3, 3, and those are consistent with the eigenvalues that we found from looking at, or those are consistent with the singular values we found by looking at the eigenvalues of the square root of t dagger t. If we compare that now with the eigenvalues of t, we found that rather quickly because it was a lower triangular matrix, and we found the eigenvalues were 0, 0, 0, minus 3 of our operator t. Those are now actually bounding or bounded by their absolute values of these eigenvalues of t are actually bounded within the minimum singular value and the maximum singular value. That's just something to keep in mind, that these singular values actually give us a size associated with the eigenvalues of our original operator. We can also find this polar decomposition. Now that we've gone this far in our example, let's go ahead and look at finding the polar decomposition of this operator t. The matrix representation of t I've written down in a small form, this 4x4 matrix on the left. We found the matrix representation of this positive operator associated with the square root of t dagger t, and that was found here. From that, we could find the matrix representation. That's now just diagonal entries 3, 2, 0, 3. We now want to rotate that with this rotation matrix S in such a way that it leads to the matrix representation of t on the left. In other words, is there a way to form the top row in the matrix representation of t using some rotation on the matrix representation of the square root of t dagger t? Well, here, really all we need to do, remember S needs to be full rank, and it has to have eigenvalues of 1 or minus 1. It's not scaling at all, it's simply rotating. We can actually generate an all zero row to form t by simply pulling out or extracting the third row in this right side matrix, which is this positive matrix, square root of t dagger t. To generate 3, 0, 0, 0 in the second row simply means we need to copy the first row in this positive matrix. So that gives us then a 1, 0, 0, 0 for our rotation matrix, and that looks good because that has a norm of 1, that vector. The first row has a norm of 1. To obtain 0, 2, 0, 0 in our third row, we can identify that that's really consistent with the second row of the positive matrix square root of t dagger t, and that's found then or positioned in t by just pulling off the second row with our rotating matrix S. And finally, to make 3 in the 4, 4 entry negative 3, we can scale it by minus 1, and that now is a way to find this polar decomposition or how do we now find the rotation matrix S? Another way that we could have found that is we see that t is equal to S, let's just say square root of t dagger t, and if I called that some m, we could actually invert m in this case because it's, or I'm sorry, let's just stop at that particular point because we really don't want to try to invert that matrix. But if m did have an inverse, we could find S by inverting m to obtain t m inverse. But that's only true if m has an inverse, and you can see that in this case it doesn't because we actually have a 0 eigenvalue for this positive matrix. So in this case we kind of had to look at finding this rotation. In this case it was okay to do by inspection. If we had a non-singular positive, a positive matrix, meaning all of its eigenvalues were non-zero, we could invert it to find S that way. In this particular example, this wasn't possible. And we'll stop it at that.